Okay guys, so this is where the fun really begins. This is the stuff that everyone seems to hate because it's worded questions. But once you've done a few of them, you start to get, you recognize the patterns that sort of occur. So here I've got a farmer has sufficient fencing to make a rectangular pen of perimeter 200 meters. What dimensions will give them enclose the maximum area? So just so that you know, if it's a rectangular shape and it says it can be a rectangular shape and all of the sides are the same length, can be the same length, it's always going to be a square. But let's prove it. So, if I draw a rectangle and I say that's x, that's y, we know 2x plus 2y gives me my perimeter, which is 200, because that's how much he has to fence. 2y equals 200 minus 2x, y equals 100 minus x. So that's our length here. So this side is x, and this side is 100 minus x. If you want to work out your domain, well, you know x has to be greater than 0, and you know that y also has to be greater than 0. However, we know that y is the same as 100 minus x. So 100 minus x has to be greater than 0. Minus x has to be greater than minus 100. So x has to be less than 100. So our domain is 0 is less than x, which is less than 100. Now, we want to get the maximal area. So the area of a rectangle is x times y, which is x times 100 minus x. Now, we know that that's the same as 100x minus x squared. If we want to maximize our area, we want to find where the function has a maximum, like a local max or our absolute max. So we find dA dx, because maximums and mins occur when the gradient equals 0. So we get 100 minus 2x, dA dx equals 0 for a max slash min. Okay, so we're going to get 100 minus 2x equals 0. We get 100 equals 2x. When I bring that 2x to the other side and make it positive, x equals 50. Now, if x equals 50, we get y is 100 minus x, which is 100 minus 50. So we get x is 50 and y is 50. So what dimensions give the maximal area? Dimensions, make sure you answer the question, are 50 by 50. Does that make sense? We've got a pen. We can have 50, 50, 50, 50. So that adds up to 200. When we multiply them together, our area is 2500. You can also check it on a graph, but we really don't need to at the moment. And like I said, it'll always end up being a square if it's a rectangular pen and you're filling in all four sides. Sometimes I'll give you like a river, and then you have to find these three sides. Then it won't be a square, because one of the sides is given. So when you maximize, it'll actually be the shape of a rectangle. Okay, two variables x and y are such that x to the power of 4, y equals 8, and z is equal to x plus y. Find the value of x and y that gives z a stationary value and show that the value is a minimum. Oh, we could have also proved that this was a maximum, but by finding the second derivative and subbing it in. Actually, let's just do it. If we find the second derivative here, we get d squared a dx squared. Derivative of that is negative 2. So it has to be a max, because when dA dx is less than 0, it's a max. So we've just proven that it's a maximum. Okay, so here it says show that this value is a minimum. Okay, so first let's get y in terms of x. So this gives me y equals 8 on x to the full. So therefore we know z is equal to x plus 8 on x to the full, or x plus 8x to the negative full. Find the values of x and y that give it a stationary value. So dz dx equals 0 for max min. We don't know whether it's a maximum or minimum yet. dz dx equals 1 minus 32, and we take 1 away from the power, negative 5. So I get 1 minus 32x on 5. dz dx equals 0, which equals, oops, what have I done there? Hang on, I stuffed that up. That is 32 on x to the 5. So 1 minus 32 on x to the 5. If I bring my 32 on x to the 5 to the other side, so I get 32 on x to the 5 equals 1. Multiply x to the 5 across. X to the 5 equals 32. And then we get x equals the fifth root of 32, which is 2. When x equals 2, we know that y is equal to 8 on 2 to the 4. 2 to the 4 is 16, so I get 8 on 16, which is, hopefully it fits, 1/2. Okay, so when x equals 2, y equals 1/2. That gives us our stationary point. We want to prove that it is a minimum. So let's find d squared z dx squared. So if I derive, there's dz dx. If we derive that, we get 0. Minus 5 times minus 32 is 160. And then we get x to the negative 6, which is 160 on x to the 6. Now, if we put in the point x equals 2, because that's where our minimum or maximum occurs, d squared z dx squared, given x equals 2, is 160 on 2 to the power of 6, which is 160 on 2 to the power of 6 is 64. All we need to know is that's positive, therefore it's a minimum. Because if the second derivative is greater than 0, then the function at that point is a minimum. Okay, so find the value of x and y that give it z a stationary value. So that's it there. And then prove that it's a minimum. That's it there. Okay, next one, a regular block whose base is twice the width, has a total surface area of 300 centimeters squared. Find the dimensions. Okay, so this is a bit confusing because we've got total surface area and then we want to find maximum volume. Total surface area of a three-dimensional shape, in this case a cuboid. We've got this side and the back side, which are 2xh, but I've got two of them. 2 times 2xh, plus I've got two ends, which are xh. So 2 times xh, and then I've got the bottom and then the top, which are 2 times 2x squared, and that equals 300 centimeters cubed. Okay, so let's expand this out. We get, it's not 4, it's 6. It's not 6, it's 4. 4xh plus 2xh plus 4x squared equals 300. This is 6xh. Bring it to the other side. No, leave it on this side. Bring the 4x squared to the other side. So we get 6xh equals 300 minus 4x squared. And we want to get h by itself. So h equals 300 minus 4x squared on 6x. Okay, so we've got our height in terms of x. We now need to find our volume in terms of x. Our volume is length times width times height, which in this case is 2x times x times h, which we know h is 300 minus 4x squared on 6x. So what I'm going to do is I'm going to change this to be 2x squared over, I'm going to bring the 6x out the front, over 6x. And then inside we've got 300 minus 4x squared. Of course, we can cancel the x's. We can take a 4 out of that bracket. So I'm going to have, if I take a 4 out, I'm going to have 8 on 6, because I've taken a 4 out, and then I'm going to have 75 minus x squared. 8 on 6 is 4 on 3, 75 minus x squared. So that is our volume. Okay, so we've got our volume, but I want to maximize the volume. So, I haven't left myself much room. dv dx is equal to, now if we differentiate this, when you differentiate 75 it disappears. When you differentiate negative x squared, you're going to have 4 on 3 times negative 2x, which is, have I stuffed something up here? 2x squared, oh there's an x on top. I'm just like, it's going to equal 0, so that's wrong. Okay, so we know how we got this, so I'm going to rub it out because I need to have some space. So from here, we know that our volume is 4x on 3 times 75 minus x squared. I'm going to multiply that 4 on 3 in. So 75 divided by 3 is 25, times 4 is 100x, minus 4 on 3 x cubed. dv dx is the derivative of this. So I get 100 minus, when I bring the 3 down, that's going to cancel with the 3 on the bottom, so 4x squared. And it equals 0 for a max slash min. Okay, we have, bring your 4x squared to the side, so 4x squared equals 100. X squared is equal to 25. X equals plus or minus 5. X has to be greater than 0. Therefore, x equals 5. So our dimensions are x, which is 5, times 2x, which is 10, times our height, which we know is, what is our height? 300 minus 4x squared on 6x. 300 minus 4 times 5 squared on 6 times 5. So we've got 300 minus 4 times 5, which is 4 times 25. That's 100. So on top we're going to get 200. On the bottom we're going to get 6 times 5, which is 30. So I get 200 on 30, which is 20 on 3. So that's what maximizes, they're the dimensions that maximize the volume. Okay, giving you plenty of examples here. A cylindrical canister is closed at both ends, has a surface area of 100 centimeters squared. Find correct two decimal places, the greatest volume it can have. If the radius of the canister, okay. So first, we've got a cylindrical canister. So we've got cylinder, cylinder, top, bottom. We know that the surface area of one of these is pi r squared. Oh, what is it? The bottom's pi r squared, 2 pi r squared. And then this here, the length around the outside is 2 pi r h. So 2 pi r h. So we can say 2 pi r plus h. And we know that that equals 100. So 2 pi r plus h equals 100. We want to get the volume by itself. So we get r plus, we want to get the height by itself. R plus h equals 100 on 2 pi r. So we get h equals, let's cancel that, 50 on pi r, and then minus r. So that's our height. The volume, let's put it all over a common denominator. So h equals, I want to put it on pi r. So 50 minus pi r squared on pi r, that's our height. Our volume is pi r squared h, which in this case, our volume is pi r squared, 50 minus pi r squared on pi r. So our pi is going to cancel, our r is going to cancel with one of them. So we end up with our volume is r 50 minus pi r squared, which is 50r minus pi r cubed. Now, if I want to find when it's maximized, dVdr is 50 minus 3 pi r squared. dVdr equals 0. So we get 50 minus 3 pi r squared equals 0. 3 pi r squared equals 50. R squared equals 50 on 3 pi. And then r is plus or minus root 50 on 3 pi. Find the greatest volume it can have. So we know our volume formula is this, 50r minus pi r cubed. 50x minus pi x cubed. And we want to do it, so given x equals square root 50 on 3 pi, I think it was. 50 on 3 pi, yep. Okay, so if we do that, it tells us that's our value, but we wanted it as a decimal. So 76.78. So volume equals 76.78. Now it says, if the canister the radius can at most be 2. So let's go and graph this function from, we'll graph it everywhere. So clear that, paste it, tick it. Okay, so zoom auto. Doesn't really give us a graph, does it? Zoom. Let's go initialize. Oh, so it looks like it happens between 0 and 4. So let's lock our ends in. 0, we could have found that as well, but we didn't. 0 to 4, zoom, auto. Okay, so we know our max is here, but if we restricted this function to be between, hang on, before I restrict it, let's just have a quick look. We know that our max, analysis gsolve max, is 2.376.776, which is what we found before. Now, if our max is at 2.3, well, then if we restrict it, and we say 0 is less than x, which is less than or equal to 2. I forgot to put my given sign in there. So now if we sketch it, and we say, okay, what's our max value? We can't use max, we've got to use Fmax, because it's an absolute max. We get 74.867. So if r equals 2, v equals 74.67. Now another way you can do it, you can go, if it ever asks for an absolute max of a function, you can just put in the function, interactive calculation Fmax, and then you say we want it between 0 and 2, because that's our maximum value. And it tells us the maximum occurs at the right-hand endpoint, which is when x equals 2, and it is 74.86, or 87 actually. Okay, we are slowly getting there. Oops, I'm going to have to talk and charge my pen at the same time. Okay, so the number of bacteria N of culture increases at a rate proportional to the number present according to that law. Find dN dt. So, where t is the number of hours growth and k and n naught are constants. So, we have n is equal to n naught e to the kt. If we want dN dt, we're just deriving this function with respect to t. So in this case here, when we derive an exponential, we derive the index or the exponent, which is going to give me k. So I'm going to have k n naught e to the kt. So that is dN dt. If it takes 48 hours for the colony to double in number, find k. So now t is the number of hours growth. When t equals 48, we know that the colony is doubled. So if n naught is our original amount, we can say n when t equals 48, n is equal to 2 times n naught. So we get 2n naught equals n naught e to the kt. Whoops, but we know that t is 48, so 48k. When we divide that n naught to the other side, they cancel. If I log the other side, I get 48k is equal to log e of 2. So therefore k is equal to 1 on 48 log e of 2. Okay, so hence find the rate at which the colony is increasing when n equals 10 to the power of 4. Okay, so what do we know? We know if we go back here, we have got this and this are the same. So we can actually say that dN dt is k times n. So if we know that dN dt equals kn, we know dN dt is equal to kn, and we know that k is 1 on 48 log e of 2. And in this case, n equals 10 to the 4. We know that dN dt equals 1 on 48 log e of 2 times 10 to the power of 4, which is 10,000. So we get 10,000 on 48 log e of 2. What's 10,000 on 48? I can't be bothered thinking. Give me that answer. 625 on 3. Log E2. And the number of bacteria. So bacteria per hour. Per hour. So that's our rate when n equals 10 to the power of 4. So when the amount of bacteria is 10 to the power of 4, it's increasing at a rate of 625 on 3 log 2 bacteria per hour. Okay, now we get on to the super fun stuff. They've started to ask more and more questions like this in exam 1 without actually I don't know, they haven't placed enough emphasis on it in the course. A cross-section of a drain is said to be an isosceles trapezium with 3 sides of length 2 meters as shown. Find the angle that maximizes the cross-sectional area and find this maximum. So we want to find whatever angle here will make this area a maximum. Now the good news is we know if we drop a line down here, here, here we have a right angled triangle. So I'm going to call this y, and I'm going to call this x. So we can work out something in terms of y and x. We know that sine theta is equal to opposite, which is y, over hypotenuse, which is 2. So therefore we can say that y equals 2 sine theta. So that length there is 2 sine theta. We know that cos of theta is equal to x over 2. So therefore x is equal to 2 cos of theta. So I can say that length there is 2 cos of theta. Now, to work out the area of the trapezium, we need this length, which we know is 2. We need the top length. Now we know the top length, well, that part there is 2. We know that this length from here to here is 2 cos theta. And we know that this length from here to here is 2 cos theta. So our total length across the top, so I'm going to write top length, is 2 plus 2 cos theta plus 2 cos theta, which is 2 plus 4 cos theta. Our bottom length is 2. And whenever we want to find the area of the trapezium, we also need the height. Now we know the height because it's over here. It's 2 sine theta. So our height is 2 sine theta. Now the area of a trapezium is a half times base plus, we say a plus b. I'm just trying to work out what it was. A plus b, where a and b are the top and bottom, and then times h. So we've got a half times 2, the bottom length, plus 2 plus 4 cos theta. So that's the bottom, and that's the top. And then times the height, which we know is 2 sine theta. Okay, so we've got a 2 plus 2, which is 4, and then we've got to halve it. So we're going to have 2 plus 2 cos theta times 2 sine theta. That's our area, which we also know is 4 sine theta plus 4 sine theta cos theta. Okay, if we want to maximize our area, we know that d80 theta is going to be the derivative of this. 4 sine theta, what's the derivative of that? Well, we know when we derive sine we get cos, so we get 4 cos theta. This second bit is a bit nastier though, because we need to use the product rule. So I'm going to say u is this, and v is this. So if I derive 4 sine theta, I get 4 cos theta. And of course I times that by cos theta. So that's u dash times v. And then if I derive cos theta, I get negative sine theta. And I times that by 4 sine theta. So we end up with 4 cos theta plus 4 cos squared theta minus 4 sine squared theta. Okay, this is pretty ugly because we've got sines and coses, but we know there's a relationship between sine squared theta and cos squared theta. Sine squared theta plus cos squared theta is equal to 1. So we can say sine squared theta is equal to 1 minus cos squared theta and replace it into here. So we've got 4 cos theta plus 4 cos squared theta minus 4 times 1 minus cos squared theta. What does that give us? That gives us 4 cos theta plus 4 cos squared theta minus 4, and then plus 4 cos squared theta, which gives us 4 and 4 is 8 cos squared theta plus 4 cos theta, and then minus 4. Now, that's what d80 theta is. Now we know d80 theta equals 0 for max min, so it equals 0. Okay, so we've got 8 cos squared theta minus 4 cos theta minus 4 equals 0. Let's divide through by 4, so we get 2 cos squared theta minus 1. If we let a equal cos theta, a squared equals cos squared theta, we get 2a squared minus a minus 1 equals 0. Then we get 2a minus 1 plus 1 equals 0. Okay, so from here we get a equals negative a half, or I must have stuffed something up. A equals 1. Something is buggered up somewhere. Because I can't have it being negative a half. Okay, so that's right. There, minus 4. When I derive cos, I get negative sine, and I times that by 4 sine theta. Yep, that's right. Okay, we know sine squared theta is 1 minus cos squared theta, so it's going to be negative 4 plus 4 cos squared theta, so 8 cos squared theta plus 4 cos theta, and then minus 4. Is that right? And there it is. I've got a plus there, and then for some reason here it's a minus, so that's a plus. Okay, so if that's a plus, I have 2a squared plus a minus 1 equals 0, 2a minus 1, a plus 1 equals 0. So you get a equals 1 half, or a equals negative 1. Okay, where can I go to? I'm going to go up to here. Now, if a equals 1 half, cos theta equals 1 half, and we know that if we've got cos theta, we've got 1 to root 3. If it equals a half, then my angle's pi on 3. Or if we've got a equals negative 1, cos theta is negative 1. So theta would equal, if you think about a cos graph, goes down and then back up. When does it equal negative 1 at pi? This angle can't be pi. It's got to be between 0 and 90, so it can't be that answer, so it's got to be pi on 3. Okay, so if we want our area to be a maximum, theta equals pi on 3, and it says to find the maximum. So I've got to find some room. Okay, so we know our formula for the area is this. So our area is equal to 4 sine pi on 3 plus 4 sine pi on 3 cos pi on 3. Okay, sine of pi on 3 is root 3 on 2, so I get 4 times root 3 on 2, plus 4 sine of pi on 3 is root 3 on 2, and then plus 4 times, times 1 half. Okay, so I get 2 root 3 plus, that is going to cancel with, stuff that up. That is root 3 on 2 times 1 half. So they're going to cancel. So I get 2 root 3 plus root 3, which is 3 root 3. So that is our maximum area. Area when x equals pi on 3. Okay, we're getting really close, which is good because I need to go to the toilet. Assume that the number of bacteria present in a culture is given by n of t, where n of t is at what time will the population be a maximum, and what is the maximum population? So, we want dn dt to equal 0. So dn dt, now if we derive 36t, we get 36 and leave that alone, e to the negative 0.01t. And then if we derive this and leave the 36 alone, we get 36t times negative 0.1 e to the negative 0.1 t. Okay, so we can take out that as a common factor and also the 36. So we've got 36 e to the negative 0.1 t. And then in a bracket, we've taken all that out, so we've got a 1. We've taken that out. We have taken that out. So I get negative 1, because 0.1 is the same as negative 1 on 10, t. Okay, if dn dt equals 0, then we get 36 minus e to the minus 0.1, and then 1 minus 1 on 10 t equals 0. So either 36 e to the negative 0.1 t equals 0, or 1 minus 1 on 10 t equals 0. That can't be 0, because e to the negative 0.1 t is greater than 0 for all t, so there's no solution. This one here, if I bring my 1 on 10 t to the other side, or t on 10, that equals 1, so t equals 10. So that's when the maximum population occurs. What is the maximum population? Well, we know n of 10 is equal to 36 times 10 times e to the negative 1 on 10 times 10. So our maximum population is going to be 360. That. E to the, that's going to cancel. E to the negative 1. So n equals 360 on e. Okay, so that's our maximum population when n equals 10. Okay, assume the number of bacteria present in a culture is given by that, where n equals that, so that's our previous question. Sketch the graphs of n of t and n of t against t. Find the maximum rates of increase and decrease and the times which they occur. So 36t e to the negative 0.01, 36x times, clear, 36x times e to the negative 0.1x. Sketch it. Zoom. Initialize. Okay, so we know the maximum occurs at 10, so let's go from 0 to 100, and then go zoom auto. So there's our graph. Analysis gsolve max. It's at 10 and then 132.43. Okay, so there's that's n of t, something like that. Our derivative, so we can just bring that down, highlight it, keyboard, oops, wrong one. Oh. 36 times 36 e to the power of negative 0.1 x. Sketch it, and then we want to sketch its derivative. So bring it down, highlight, keyboard, ddx. Okay, so our derivative looks like that makes sense. It's steep there, so it's going to be up high. It goes down, and then it flattens out. It approaches 0, so it doesn't actually go above the axis. So it just goes like that. Okay, so our maximum occurs here, which is where the derivative equals 0. Find the maximum rates of increase and decrease of the population and the times at which they occur. So the rate of increase is dn dt when that's got a maximum. So when does this have a max? And then dn dt, when does it have a min? So we can find out by sketching the second derivative and saying when that has a max and a min. So second derivative, x squared, oops. Okay, so if we get rid of these two graphs, analysis G solve max. So it has a max at 30. The maximum gradient is when x equals 30, and the actual rate of decrease, well, we got to put that into the original function. So we want to find, sketch it, we want to find analysis G solve ycal when x equals 30. So our maximum rate of decrease is, that's increase, I think. Yeah, maximum rate of increase. And then your other point, analysis G solve and min of the green graph. There is no minimum. I can see it's, we can go out to here, paste it. Okay, calculation f min. So does this function ever have a minimum? It occurs at negative infinity, so it goes down forever. But if the assumption is, when is the maximum number present? The maximum rate of decrease occurs when t equals 0. Because that graph, it's an absolute value, because the minimum occurs right there. So that's when the maximum rate of decrease occurs, at that point there, which is when t equals 0. And the actual rate of decrease, if we go into here, and we do that, and say given, well, that might be the rate of increase. X equals 0, it's 0. So we want the rate, so we want the derivative. So d dx, given x equals 0. So that's the maximum rate of increase, and the other one's a maximum rate of decrease. Okay, so that's that chapter over with. Thank God, it's a long chapter. Lots of questions.